So the next digital circuit that we are going to consider for the design of for writing a program and gate level modeling is the design of 4-bit ripple carry adder. So when you consider a 4-bit ripple carry adder, it is otherwise called as 4-bit parallel adder, where it is going to consist of two numbers A and B, and A is of 4-bit in size and B is of another 4-bit in size. And we try to add these two numbers A and B, which is of 4-bit in size. Let me take the A as A3, A2, the bits of A as A3, A2, A1, A0, and the bits of B as B3, B2, B1 and B0. And we are going to try to add the two 4-bit number. So when we try to add the two 4-bit number, what actually we'll be doing is, we start the addition from the LSB. So we'll be first adding this A0 and B0, and the result will be taking it as sum and the carry as S0 as sum and the carry C0 as the C0 is going to be taken carry over to the next highest bit. And we are going to add C0 carry and then A1 B1, and the resultant bit will be the sum, which is denoted as S1, right? And then the carry again is carried over to the next highest bit, and which will be added together here as a 3-bit addition, and then the sum will be denoted as S2. Carry again is moved to the next bit, which is going to be getting added with your A3 and B3. So the sum will be considering it as S3, and the final carry we get it is C out. So totally when we add two 4-bit number, the result will be of 5-bit in size. So the 5th bit will be, the MSB will be taken as the C out, the final carry, and the remaining 4 bits will be considered as the final sum. So now while addition, when you see here, the first LSB bit A0 B0 requires 1 half adder, and the other additions requires 3 full adders. In order to make it as a uniformity, what we do, we are going to insert another bit which is called as C-in bit, and this C-in bit will be always tied to 0, and then we make it as a full adder here. So we are in need of 4 full adders in order to design a 4-bit parallel adder, otherwise called as the ripple carry adder. So 4 full adders are required to design a 4-bit ripple carry adder. So the structure of that particular ripple carry adder is given here, where the first full adder is FA0, then FA1, FA2 and FA3. So for the first full adder, the inputs are Cin, A0 and B0. So A0, B0 and Cin are connected as the input for the full adder 0. So the output of the full adder 0 you consider is the sum S0. So S0 sum, and the carry will be propagated to the next bit. So hence we are transferring the carry, which is termed as C0, to the next full adder FA1. So the inputs for the next full adder are A1, B1 and C0, and the outputs are S1 and then C1, where C1 will be propagated to FA2, and the inputs are FA2 are A2, B2 and C1, and the sum S2 and the carry C2 will be the outputs of the full adder 2. So the sum C2 is again now moved on for the next full adder, which is full adder 3, and the inputs for full adder 3 are A3, B3 and C2, and the sum will be taken as the output S3, and the final carry will be considered as C out. So totally we will be getting 5 bits as the output here in the ripple carry adder, 4-bit ripple carry adder. And the block representation of this 4-bit ripple carry adder comprises of 2 inputs AB, which is of 4-bit in size, 1 input again Cin, which is of single bit in size, then sum is of again 4 bits, and C out is a single bit. So totally we will be having the inputs and output representation given in this block representation of the ripple carry adder, right? And now we will be starting writing the program in gate level modeling for this particular structure. It will be otherwise called as structural modeling, where we are going to call full adder or instantiate full adder 4 times, because we are using 4 full adders in this design of ripple carry adder. So already we have done a program where I have used the module name as full adder for designing a full adder in gate level modeling. So that particular full adder, keeping in mind that particular full adder is already, it will be already compiled. The full adder has been already compiled and then simulated without errors. We have in ready with the hand this particular full adder which is already done, right? So we are going to use the same full adder in our program to write a program in structural modeling. We are going to call full adder, instantiate full adder 4 times here, right? So the every program starts with a keyword module, right? And then we have to give a module name, where I can give the module name is RCA4. The module name for this is RCA4, right? And the output and input. So the output here is sum first and then Cout. The inputs are A, B and then Cin. And coming inside, we have to declare the output. So the keyword used to declare the output is output. And when you consider sum, it is of 4-bit. Carry is of single bit. So we cannot directly write the sum and Cout in the same line of output declaration, because sum is a vector declaration. Carry we have to declare it as a scalar, as a single bit. So hence, first I will define the sum as output 3:0. We will be having sum, where first is the MSB position 3 and the next one will be the LSB position. So if we declare like this, then the sum will take 4-bit positions here. And the next one we have to declare the output, which is the Cout, which is scalar declaration, and hence we simply say output Cout. So if we declare like this, then Cout will take a single bit representation. If we declare by defining the size of the bits like MSB colon LSB, then it will go for a vector declaration. The next one AB, again here AB has to be declared in vector. So the keyword for input is input. Then the size of A and B is 4-bit in size, and hence 3:0 A comma B. So both A and B will take 4-bit of size. And the next input declaration is the input carry Cin, right? And always we have to maintain the input carry Cin to be 0 for this particular full ripple carry adder, right? And now after declaring here, we have intermediate lines like C0, C1, C2. All these 3 variables has to be declared as a wire, because it is not an input, not an output. Intermediate values of carry transferring from one stage to the other stage of full adders, and hence we declare those things as wire. So wire C0, C1, C2. So all these we have declared as a wire, right? Now once we have declared the wires, then we are going to instantiate full adder, which we have already designed using gate level modeling 4 times in order to design a ripple carry adder, right? So the module name that is already given for the full adder is full adder only, and hence full adder. The instance name for the first full adder is FA0. So full adder FA0. The module name of full adder and the instance name which I refer to this particular full adder. So it is FA0, right? Now within bracket we have to list the outputs and the inputs. The order in which you have to list the outputs and the inputs are, it has to match with the module of your full adder already we have designed. So in the already we have designed full adder, we have the order as sum, carry and then the 3 inputs, right? So same order we have to maintain. So now when you consider full adder 0, the sum output is denoted as S0, carry output is denoted as C0 and the inputs are A0, B0 and Cn. So we are going to write the sum output S0 as S within square bracket 0. Directly we should not write it as S0 because the sum here, sum is denoted as sum, right? So we have sum within square bracket 0. So see here, since sum is of a declared as a vector notation, we have to use a square bracket to access each and every bit of the sum. So sum within square bracket 0 represents sum of 0, right? And the next one, comma. The next output is the carry output denoted as C naught, and the inputs A naught. So A square bracket A of 0, then B of 0, and then finally the input carry Cin. So in this order you have to instantiate your full adder. The next full adder is the full adder 1. So full adder, the instance name is given as full adder 1, and then we have the sum output as sum of 1, then the carry output as C1, right? And the next one, the inputs for full adder 1. The inputs for full adder 1 is A0, A1, B1 and C0. So A of 1, B of 1 and then C0. So these are all the inputs for the second full adder 1. And the next one, the third instantiation, full adder, and we are going to refer full adder 2. So in full adder 2, the output is sum 2 and hence we have sum of 2 and the carry output is taken as C2. The inputs are considered as A2, B2. So A of 2, comma B of 2, and then the last input is C1. And the next last full adder we refer to is full adder 3. In full adder 3, the sum is S3. So here we consider it as sum of 3. And then the final carry, which is denoted as C out. And the inputs for full adder 3 are A3. So A of 3 and then B3, B of 3. And the input carry here is C2. So we have instantiated 4 times the full adder as FA0, FA1 and FA3. And finally, we end the module by using the keyword end module. So this program is a structural level program for the designed 4-bit triple carry adder.